Are there any questions? Anyone about to come up with a question? Then I'm about to come up with a question. Bless you. All right. Similar to the car problem, except there's some information I did not write down that you're supposed to be able to pull out of the information there. Because the car problem or ball or whatever object I used was moving horizontally, at least that's the way I pictured it in my head. And in this case, we have it now moving vertically. So, let's start out with what do we know?
How fast or how long it fell?
Okay, and which is, all right, so we know that piece of information. I'll just write a little brief note over here. Time is equal to 5 seconds. Or for the purists out there, delta T equals 5 seconds, whichever way you like it. And what else do we know?
It was dropped.
Okay, so what does dropping mean?
I guess the direction.
Oh, okay. So what's the direction? Okay. So it's going to be going down. There's one other thing that dropping means. Okay. As opposed to what else?
Throwing.
Okay, or throwing it down, either way. So it's dropping, it's being dropped as opposed to being thrown. What's the difference between dropping and throwing?
It's going down towards the earth.
Yeah, but that's going down towards the earth, but would you consider that I dropped it?
No, you threw it down.
Okay, so what does dropping tell us?
I mean, it's falling kind of slow because it's just being
All
dropped.
constantly.
Almost there. What was the, falls constantly? So, somebody said something. Falling constantly is vague, so I don't know if something else was said. If I drop something, how fast is it going at the beginning? And that's the difference. If something is dropped, it immediately implied that the initial velocity is 0. Write a little abbreviation here. Initial velocity is 0 meters per second. All right, we got one other piece of hidden information there, something that's not written down explicitly, but you are supposed to pull out of the information. Camera too much in the way?
Oh, they're kind of my favorite.
Earthquake. All right, so why did I bother writing near the surface of the earth?
It gives us, how like relatively how far it fell. If it's like kind of near, then you don't got that far to fall.
Yeah, well, near the surface of the earth could be 100 miles. I mean, that, relative to the size of the planet.
Acceleration due to gravity.
That's the thing. The difference a big difference in a problem like this and a problem of, a car's moving along a road is that there is an assumption of the acceleration in this case that I don't have to write down. Now, it is location dependent. I just said near the surface of the earth, which tells us that the acceleration is what? Say the whole thing.
47.
Oh, I'm looking for units.
Square.
There we go, yes. In which direction is it accelerating? So acceleration as a vector would be positive since, well, actually, is it positive or negative? We haven't established that yet. Okay? You don't have to do it with a question mark, you can just make the statement. There we go, all right. We could have made it down negative, that's fine, just be consistent whatever you do. So acceleration is positive, 9.8 meters per second squared. And that number for Winston-Salem is 9.798 meters per second squared. For Mars, about 3.5 meters per second squared, somewhere in there. Venus, I think it's 8.9 meters per second squared-ish. The Moon, 1.6 meters per second squared. All right, so it starts out at 0. The velocity changes by 9.8 meters per second every second for 5 seconds. Now, Hewitt gives you a formula, and we'll do the formula second. But, well, we've got time, 0, 1, 2, 3, 4, 5. And velocity, in meters per second. So after 1 second, what is the velocity? After 2?
29.4.
Say it again.
29.4. 39.2. 49.
All right. So notice that basically we're adding 10 and subtracting 0.2 every time. All right, so we know how fast it's going, so that answers the first question about how, actually we answered the second question, how fast it's going after 5 seconds. How far did it go? And we did problems very similar to this on last week. Or how would you approach the problem?
Find the average velocity,
Okay, what's the average velocity?
49 divided by 2.
Yeah. So again, to find the average, if acceleration is constant, all you have to do is average the first and last one. So the average velocity, 0 plus 49 divided by 2, which is 24.5 meters per second. All right, so I know the average velocity. Now, how do we figure out how far it went?
Divide by the time.
If we divide by time, then we'd end up with meters per second squared.
Times.
There we go, I heard the magic word.
Multiply.
Yes, multiply. On average, we're going 24.5 meters every second. Well, how long do we do it? Well, we did it for 5 seconds. So 24.5 meters per second times 5 seconds. And we get 122.5.
Yeah.
And we are missing one last thing.
Meters per second.
Meters.
Meters. Now, I think I said how far does it fall? I mean, and when you say how far, that's a distance. But we were using the equations we use for displacement. But since it's only traveling in one direction, the magnitude of the displacement is just the distance. So we don't have to worry about, at what point did it stop and then turn around. It's a simple problem in that respect. Now, in chapter 3, Hewitt gives some equations for this, but I don't think he states the assumptions as explicitly as I would like him to. So one assumption is acceleration is constant. And if the initial velocity is 0 meters per second, then he gives the formula that he does speed, but works for, we'll just write up, that's the formula that Hewitt gives. And so G is just the acceleration due to gravity, 9.8, times time, which is 5. And that's what we did, doing it by just adding 9.85 times. And you end up with 49 meters a second. The other formula that he gives, again, with the same two assumptions, is that the distance it falls, I think he actually writes the word distance out, 1/2 GT squared. Again, starting at rest. The car problem we did on Thursday, we did not start at rest, so we cannot have used this. So it's 1/2 times 9.8 times 5 squared, which I assume is 122.5. But suppose, questions up here before we suppose?
That equation for distance, you can use it just for this specific problem, or like across the board?
All right, so this is specifically, you drop an object and it falls because of the acceleration due to gravity. We can make it slightly more general. If the assumption is that the acceleration is constant, we actually could also just use that the speed is acceleration times time. Or we can make it slightly more general, where the velocity is acceleration times time. Again, it assumes that you're starting at rest. And the other equation, the displacement 1/2 AT squared. And again, acceleration is constant. And the initial velocity is 0. Other questions? formulas that I give on the tests are, and some of the master sets, are the ones that are in the book, in the summary section, or in the plug and chug section. And I'm pretty sure I also have these as well, because the ones with G in it are the ones Hewitt gives, and then the more general version right here. Now this next bit, I offer to you because in the past when I've done this, some students have taken it and used it well. The next equation I'm going to give you is not crucial for solving any of the problems. It's just, it'll save you some time if you happen to remember how to use it. Now, if you have an object that does not start at rest, there is a general formula which is related to some of the stuff that we have here. Let's see. That's the average. So here we had displacement is equal to the average velocity times time. That's what we did here. So this has the assumption of either you're dealing with average or acceleration is zero. So velocity average or acceleration is zero. That's supposed to be meters per second squared. So here acceleration is zero, velocity is constant. Here acceleration is constant, velocity is zero. If you are starting out with, if you still have acceleration is constant, but velocity initially is not zero, the equation is actually just a combination of those. What I mean by that is that the displacement is equal to the initial velocity times time plus 1/2 at squared. That is the more general, slightly more general version of basically the two equations that Hewitt gives. Go ahead and use it. In the problem on Thursday, what was the initial velocity? I'm trying to remember the. Let's see, initial velocity, time, acceleration. All right. Does anyone have the numbers from Thursday?
Positive 20 meters per second.
Positive 20 meters per second?
Yeah.
Okay.
And then acceleration was negative 6 meters per second squared.
Okay.
And time was 12 seconds.
And what did we end up with as the displacement?
Negative 192 meters.
All right. So we got to that negative 192 meters by figuring out what the final velocity is, finding the average velocity, and then multiplying times time. But if we plug straight into this equation, we have 20 times 12 plus 1/2 the acceleration times 12 squared. So that's 240 minus 144 times 3. Minus 432, which is negative 192. So, if it works for you, great. If you can't remember it, or just one equation too many, we got other ways of doing it. As demonstrated on Thursday when we got the same answer differently. Absolutely stunning, right? Is there anything physics can't do? Physics can do everything. Mostly build weapons, but besides that. Alright, we've done all that stuff. Questions? Sushil?
Could you do something similar to number 8 on homework? Or the master's?
Oh, on the master set 8, what was the problem on 8? Was that the vase dropping?
Yeah, the vase dropping.
It'll be completely different, it's a rock this time. A rock falls 20 meters. Near Earth. Is dropped. It falls 20 meters near Earth to the pavement below. It, after hitting the pavement, the rock stops